Welcome students. We want to discuss about triple integral today. Before we go on to triple integrals, let's revisit the double integral. So recall if you have a function f, uh, the graph of function f is given on domain D like this. Then the double integral is given by f of x, y, dA over region D. So this is an expression of integral. Now to compute this integral, to compute I, we need to express I as an iterated integral. Iterated integral and to do that, which requires, and this requires what? This requires geometry of footprint. Here by footprint we mean the region D, the footprint D, and we want to understand that understood in terms of inequalities. In terms of inequalities. So what do I mean by that? So let's take an example. Suppose I want to integrate 0 to 1 x to 1 of sine y square dy dx. So in this case, I've already written down my region D. So I've already written down my double integral as iterated integral. So if I want to draw my region D, so my y hits x first, then y hits 1. So in this direction, y equals to x to y equals to 1, and my x changes from 0 to 1. So this is my region D. I should just write D there. So we need this region D so to be able to write the iterated integral. However, note the following: this integral cannot be computed directly, right? Because well, sine y square does not have an elementary antiderivative. So what we'll do is we'll reverse the order of integration. So for that, we can see that your region D, when you write it in terms of as x first, your x changes from 0 to y, and your y changes from 0 to 1. So you see, first of all, that we need the geometry of footprint D, which is understood here. So the geometry is understood through this. And it has to be understood with the inequalities as we have found out here. So this is how we understand the whole integration, double integral, okay? So now let's understand the similar thing about triple integrals. But before that, note the following. So suppose I want to compute the volume. So let's talk about 2D volume. So 2D volume of this under this object is, so volume of this object here. Yeah. So volume of 2D volume is integral D f of xy dA. Now that can be written as integral d 0 to, instead of f of xy, I'm going to write 0 to f of xy of dz, right? dA, right? So you have essentially found out volume of this solid. Let's call this solid as E. So this solid filled E. So your V, so we have found out the volume of this solid, and the region of integration is, we're calling it E. So E is x, y, z, where my xy comes from D and my z is between 0 and f of x. So interesting point is that you are looking at 2D volume as triple integral. So there are three integrals, right? Triple integral means there's a triple integration, and I can write this as, say, integral E dV. Okay, so instead of dA area element, we have a volume element, right? Okay. So first one is the triple integral in a box. So triple integral in a box on a box. So if you are considering the triple integral on a box, so on a box, so your x changes, so your x is between A to B, your y is between C to D, and your z is between R to S. So in this case, you have this integral dV has six possibilities really, right? It's dx, dy, dz, or it could be dy, dz, dx, so on, right? You can think about it like three objects and there are three spaces, right? How many different ways can you arrange them? So six ways, right? So there are six possibilities really for dV. And so we get what? We get, in that case, we get triply iterated integral and this is nothing new, right? So not a new setup. Why? Because, well, I mean, instead of doing two, so doubly iterated integral, you do a triple iterated integral. That's not going to change anything. However, things become interesting when we talk about triple integral over 3D non-box region. As we have one here. So you want to integrate, suppose we want to integrate E of f of x, y, z dV. So we want to integrate this function over this solid E. How do we do that? So in this case, if you notice, your solid E can be written in the following form. So the way E is described here for us is E is x, y, z. your E has Z between u1xy to u2xy. Then we have xy belonging to region D, right? So this thing is called the footprint, right? So it's a footprint of your region of E in xy plane. So this is a footprint. So essentially now your integral I, instead of being a volume or triple integral, is going to be, now I can be written as double integral D, and the inside integral can be consumed as V go Z going dz, Z going from u1xy to u2xy. And then once this integral is computed, you compute dA. Now it makes sense. D is an xy region, so you will when you evaluate this inside integral, you will get a function xy which can be evaluated. Now, however, your D is in special form as well. So how does your E looks like? So now let me write down the whole E in terms of inequalities in x, y, and z. Again, why are we doing that? Because to compute the triply iterated integral, we need bounds on each of those variables, right? So x, y, z. We have in this region, we can see that it is, so D is x first region, right? So we have here, let me write, your z is between u1xy to u2xy, and my x is between h1y to h2y, and my y is between C and D. Okay, so this is your region. So this is your dA, and that dA is over, this is over what? This dA is over footprint region. So again, the idea is, so when you want to compute the triple integral, the recipe is you need to find out the footprint region. But before that, you need to find out between what variable, which variable to go first, right? So this is an example of Z first or Z simple region. So how do we go about triple integral? So here again, we have a Z first region. So we have Z simple or type 1. So when we call such a region as, so suppose I'm given this solid, and I want to decide whether it's Z first or not. So what happens is the following. We call a region as Z simple if every line parallel to Z axis. So the intersection is, this is the intersection, right? With the solid. And that intersection has to be a single line segment. That means what? That means if that is the case, for this xy, your z changes from here to here. That means for this xy, your z was between the HB, which is a short for bottom curve surface, and then here you have top surface. So this is what should happen. Then we say it's Z simple. Okay. Now example of a non-Z simple region would be take this solid and have something top of that again like that, right? So this would give me an example of if my new solid is E1 union E2, then it's not a simple solid, right? It's not a Z simple solid. So anyway, so that's the idea that if you take any point in this D and you intersect, if you take a line parallel to it, parallel to Z on top of xy, it should intersect in single line segment. Okay, the intersection should be in single line segment. In that case, we have z is between this, and then the remaining your xy belongs to d, and hence the integral will look like what? First, inside integral f of x by z dz with limits hb xy to ht xy, and then whatever we get is a function of x and y, and that is integrated over region D. So this is the idea behind the triple integral. Okay. So now we should ask the question, how would we set up a triple integral? So suppose you have a region E here, which is a three-dimensional region. You want to compute the integral of f dv. How would you compute it? So first thing to realize is that if you're given that, say, suppose it's an x1 first region, right? So x1 first region means your x1 is a function, lies between function of x2, x3. Okay, so this one is like say top, and this is the bottom, right? So then what we do is the following. Once we have that idea, we first see what is the projection or the shadow or the footprint of this region E onto the x2, x3 plane. So we find out that that projection is D. Yeah. Now, once you have that, we want to recheck, are all the sides parallel to x1 direction? So we have, so what are the sides? So sides are, sides exclude top and bottom. Yeah, so sides exclude these guys. So are these parallel to x1 direction? Yeah, and they are, and such a thing is called a cylinder, right? So it's basically a cylinder. And if they are parallel, that means they will not involve x1, right? And if they do not involve x1, that means they do not, that means you can express the sides. Sides will not have x1 as a defining equation. Now, sometimes it may happen that there may be no sides. Like say, for example, you take a paraboloid like that. So the top is this side, bottom is this thing here. So there's no sides. So no sides is also a possibility. Okay. So first steps, again, what are the steps? Footprint, then check sides are parallel to x1. Third is, does E has top and bottom in x1 variable? Yeah, the answer is T should not have representative. So T can be written, so the top and bottom should be written as a function of x2 and x3, no x1, all right? So as in this case. Then once all is done, once this question is answered, then you see what is your plan for integration of this 2D region in x2, x3, right? Whether it's y first, x first, or neither, or you have to use polar, right? So we have to basically come up with a strategy for the integration of the 2D region. Okay, so this is how it goes. So let me give you a few examples here. So this was example of Z first. Again, look at this region. This is an example of your X is between U1 and U2, right? And your Y, and then you basically have check the other things. So the footprint is D, the sides are parallel to X direction. Yes, indeed they are. You see, so these sides are parallel to x direction. Then does E has a top and bottom in X variable? In this case, X1 is X. So yes, it doesn't. It should have in X2 and X3, which is Y and Z variable. So your top and bottom can be written in terms of U2 Y1 Z for the top, U1 YZ for the bottom. So so it does has top and bottom. Now the last question too is, what is the integration plan for 2D? Well, at this case, we don't know the special space shape of D, but nevertheless, I can write this as integration over D, and the inside integral is for D, depending on whether I'm computing F or I'm computing Z. So let's say I'm computing F integral of, suppose I want to compute integral of F dV, right? So then in that case, we'll have from dx, dA, and then we have what? From u1 yz to u2 yz. Similarly here as well, let's look at the following again. So this is a region D, right? So what is the footprint? We already saw what the footprint is. Are the sides parallel to the x1 direction? In this case, your x1, or this is y first, so your x1 is y. The sides are indeed parallel to this direction, right? So it is a cylinder, right? Then you have to see if the top and bottom have x1 variable, are written in not y variables. Yes, they are written in x, z, and xz variables. So your top and bottom, you can write this region E if you want. E in this case is x, y, z. Your x and z belong to D, this projection here, and then your y is between, so y is between u1, y is between, let me write it here so that E equals to x, y, z. Your x, y, sorry, x, z belong to D, and your y is between u1 xz to u2 xz. All right. So this is a setup. Now let's look at this problem. So evaluate this triple integral square root of y squared z squared dv, where E is a region bounded by the paraboloid x equals to y squared plus z squared and plane x equals to 4. So let's draw this. So x equals to y squared plus z squared is a paraboloid, a circular paraboloid opening in. So this is my x, this is y, and this is z. Trying to be consistent with the right hand rule, I've changed the orientation so that you can see the graph properly. So if you look at this guy here, so this is how the shape looks like. So it's basically the top is x equals to 4, and this is given by x equals to y squared plus z squared, right? And so again, let's follow our steps. So what do we need? We need to integrate this. First of all, we need shadow slash projection in x2, x3. Before that, we decided already what we're going to do first. So this is x first, right? Why is that? Because your x is between, so x is greater than equal to y squared plus z squared, and this is greater than less than equal to 4. So then we have, now what is the projection of this? So if you look at projection, of this as a disk, D, so D is X, sorry, not X anymore, right? D is going to be Y and Z such that Y square plus Z square is less than equal to 4. All right. So now what is, so the first thing is the footprint in YZ plane. Now, second thing to consider is, are all sides parallel to x1 direction? So question, let me ask this question here, are all sides? Note that these do not include top and bottom. Top and bottom surfaces. So all sides parallel to x-axis. And the answer is yes. And why? Because there are no sides. Since there are no sides, there are no sides. There are no sides. So in that sense, this statement is vacuously true. All right. Third, let's look at the third part. Does E has top and bottom in x1 variable? I should say whether it has an x2, x3 variable, right? That's better. So 3 does, so let me call this as 1A, 1B, 1C, right? That's what we've been doing. So we call that as 1A, B, and C. So what is C? The top and bottom are in YZ variable. So R top and bottom in YZ variable, and the answer is yes again, right? The bottom is Y squared plus Z square, and top is 4 constant. That means, so let's proceed to write down the integral. So my integral I is again over region D, which we have written on top there, of first variable. So first is with respect to x of y square plus z square from the bottom curve, which is, sorry, not curve, it's a surface, bottom surface, which is y square plus z square to 4, and then dA. And this will convert now to integral d, integral of x, dx is x, y square plus z square. And of course, we have y square plus z square here, to 4 dA. So let's write that slightly neatly here. So we have integral over d. When you put upper limit minus lower limit, you get square root of y square plus z square times 4 minus y square plus z square to the power times square root of that, that will be power 3 by 2 dA. Now to solve this, you should realize that we are in yz plane, sorry, yz plane, right? We are in yz plane, and this is a x square plus y square equals to 4. And now it's totally a problem of double integral now. Now in this case, we can use polar coordinates, right? That would be more suitable, right? So we can write d in polar will be r comma theta, where your r, so it's a circle of radius 2, so 0 to 2, and theta goes from 0 to 2 pi. That makes life pretty easy here. So we get, so the integral I becomes, so r, so it's a polar rectangle, so you have 0 to 2 for r, theta goes from 0 to 2 pi, 4 times r minus r to the power r squared to the power 3 by 2, which is going to be r cubed. Then we have r dr d theta, right? This is your area element, right? So in this case, you're really doing the substitution, y equals to r cos theta and z equals to r sine theta. And then you can finish off the integral, right? So now this is you can separate the integrals even if you want to. So 0 to 2 pi d theta, 0 to 2, 4r minus r cubed r dr. Okay, so this is how we look at the triple integral and solve it. Now the next problem is we have the following figure. It's a 3D figure. We have E is this solid here now, and we want to basically uh, rewrite this integral into equivalent iterated integrals in 5 other orders. Okay. Well, why would one do that? Well, there are many reasons for that. One reason could be that it is not integrable. You had to change the order of integration. So let's investigate this. So first, let's investigate it from y first perspective. So y first. So in this case, your y changes from, so you have to have a, so your y changes from, so first of all, what is the footprint? So if you're looking at y first region, is it, first of all, is it a y first region? And the answer is yes. Why? Because your y is between 0 to 1 minus x. Yeah, that's where your y is. Then what we have is, right, I mean, like the first region, the bottom region is here. Let me just draw the bottom region. So this is your y first. So the bottom curve is here. Right, so this is the bottom curve, and the top curve is, sorry, I keep saying curve, it's surface, right? Or top function is this one here. And the bottom function is this one. So your y changes from this to this, so it's a y first region, yes. Now first is to look at the footprint. The footprint lies in D, which is y equals to 0. So footprint is all yz, sorry, yxz, right? Because footprint is in xz plane. So it's all footprint D is all xz, such that what do we have is, if you look at this region here, we can see that this region is consisting of this part here. So how do we write that down? That is, z is less than equal to 1 minus x squared. So you can think about it in z. So shoot an arrow in z direction. It will first hit z equals to 0 to z equals to 1 minus x squared. So z equals to 0 to 1 minus x squared. And then what about your x? X goes from 0 to 1, right? So x goes from 0 to 1. X goes from 0 to 1. And we have 1b. So what is the bottom and top? Top, we have already written that here, but it's a good idea to follow this 4-point program, namely, so this is one, so this is 1b, actually it's 1c, so let's write that down. So it's 1c, we skipped ahead of our program really. We have y is between this and this, right? So this is 1c. Now what about 1b? What about the sides? So what are the sides we have, right? So we need to investigate the sides. So sides. For the sides, ignore what? Ignore the top and bottom curve. So what are the sides? The sides are, so let's look at sides here. So what are the sides? So these are the sides, right? So this is one side, and this is another side, and this is a third side, right? So these are the three sides, right? So this is a side, this is a side, and one behind is a side, right? So sides are, what are the sides as faces? So the sides as faces are, well, one of them is x equals to 0, z equals to 0, z equals to 1 minus x squared, right? Right. So this surface, for example, is z equals to 1 minus x squared. What about this side? This side is z equals to 0, right? Z equals to 0. And the back side is, the back part here is is basically x equals to 0. So these are the, so there are 5 faces, these are the 3 sides. 3 sides do not depend on y. Y, so it's a 3D region, and this 3D region is a y-axis cylinder. Some chopping of it, but yeah, so think about it. This is like a cylinder, and then it got chopped here, right? Now second one is taking care of 2D, right? So now second is 2D integral. So we have dA equals to what? dA equals to dz dx, or we can take dA equals to dx dz. So in that case, we have, if we do dx dz dx, we get, in this case, our region D can be written as xz, z is between 0, 1 minus x squared, and x is between 0 and 1, right? So in that case, the integral can be written as, now we can write the integral e dvf dv is going to be So this is what y first. So let's first write y first. Y first. F of x, y, z. Y first. Y is in form what? Y changes from 0 to 1 minus x. Then double integral over region D of dA. And now we have already figured out what our D is. It's going to be triple integral. So 0 to 1 minus x for inside f dy. I'm going to write it in short. And then my z is, then it's my z, and then it's x. X changes from 0 to 1. Z changes from 0 to 1 minus x squared. So this is your integral. So this is y first, and this is the form which is already given to you, right? So now, what if we had to write this region in terms of, so we have, let's look at the projection of this. I want to look at it as on an xz plane. How does it look like? So in xz plane, it is a form, the following form. This is my region D, and it was, this is z equals to 1 minus x squared. This is your z-axis, this is your x-axis. Now I can write my region D. So this is what z first. So I can write my region D also in, so region D at this moment here, at this moment here is z first, right? I can write down my region D as x first. So shoot an arrow in this direction. So we have my x changes from 0 to 1 square root of 1 minus z, right? So how do I change it? I bring it on the other side, and since it's positive, and my z changes from again 0 to 1. So this is again my region D can be written. So 1, 2, I could have also rewritten my integral in the following format. We could have written it as again y first, 0 to 1 minus x, then f of x, y, z. So let's call this as I. I can be rewritten in also in the following format. Y first. Now I'm going for x first after on the 2D region D, which is going to be, x is going to be from 0 to square root of 1 minus z, and then I go for z goes from 0 to 1. All right. Now similarly you can do, now we can do for this region D, we did here y first. We could also do x first and z first. Now x first is interesting because it's kind of a very interesting hybrid region. Okay, so you should look at that, x first. And that's a very interesting region. You should look at it. Okay. Right. Thank you for your attention.